the negative reflects the function in the x-axis, and then it's been compressed by a half, but then at the same time it's been compressed horizontally by a third. Okay, so where it would have been a half here at x equals 1, here it's been compressed to a third of its horizontal distance. So that is where this point here at a half would have been at x equals 1 and y equals negative a half had there not been a horizontal compression of 1/3. Okay, and then when x equals 4, the function would have been, instead of being 2, would have been at 1, but then it gets compressed to a third of its horizontal distance from the origin. So that means that this is that next point that originally was at x equals 4 and y equals 2. Okay, so that original point here ends up being right here. Okay, so it's sort of being combined, a vertical compression and then a horizontal compression sort of at the same time after the reflection in the x-axis. Okay, so that's the function after those transformations have been applied. Now if we look at B, here's the original function. There's two arms to it. Here's one arm. When all the x values are negative, that means that all the y values will be negative, because it's just 1 over all these negative values, which will make the y values negative. And then over on the right side of the origin, all the x values are positive. When you have 1 over positive values, all the y values will also be positive. So this thin line is the original function 1 over x, and then when you have a translation of 2 units to the right and then 1 unit up, all the points on this original function get translated to the right 2 and then up 1. Okay, so then this thick graph is what results. And as you see, the horizontal asymptote here of the original is y equals 0. The horizontal asymptote of the transform function is going to be y equals 1 because it's been translated up 1 unit. Okay, and then the same thing, the vertical asymptote for the original is x equals 0. Because the translation to the right 2 units, then the vertical asymptote of the transform function is x equals 2. Okay, and then now let's move along to this next example. We want to state the transformations applied to the parent function. The parent function, as we see, is 2 to the x. That's an exponential function. This little box, my printer didn't print that out properly. That's just a dot for multiplication. So it's 3 times 2 to the negative x plus 1 minus 5. The negative has already been factored out of the x term, or the x part of the function, so we don't have to do anything with that. So now we just have to go left to right and work out all the transformations. Okay, so what does that 3 do to the original parent function? Okay, so that's a vertical stretch by 3. Then, so now this is the base of the original exponential function, so you just leave that alone. That is part of the parent function. So now we go up into the exponent, and we see that there's a negative there. What does that negative do there when it's up in the function in with the x? Okay, so that's a reflection in the y-axis. Then what does that plus 1 do in here, in with the x? That's a horizontal translation to the left 1 unit. Okay, and then what does that negative 5 do there? That'll be a vertical translation. Down 5 units. Okay, moving along to the domain and range for these functions. First of all, let's identify all these functions. So identify what kind of function this is. Then, so you've got the shape of it in your mind. What does the sign of the lead coefficient tell you? Okay. Now with that, because it's a quadratic, it's a parabola, it opens down, you're probably going to have to factor this or even complete the square to get an idea of what this graph looks like, so then you can actually tell what the domain and range are. I mean, there's different ways of doing it, but I think graphing it would be easier. As I'm a visual learner, that's what I would suggest. So show you that graph in a second. Then y equals cos x minus 1 is the second function. Think about what that function looks like and what that negative 1 does to the original function cos x. Okay, so I'll show you that graph in a second. And then take a look at, here's another exponential. What does that negative do up front? Okay, so I'll show you these graphs now. Now what you should do is graph these functions yourself and then verify before I show you the functions now. So here's the graph of the quadratic, and I just graphed this using software. And so for the domain is obviously x. Okay, is a member of all real numbers such that, actually there is no such that, it's just a member of all real numbers. The range is y is an element of all real numbers such that y is less than or equal to 4. Okay, because the greatest value of the quadratic is 4 at the maximum or at the turning point, and all the other y values are below that. Then we look at part B here. Oops, sorry. We take a look at part B. And again, the domain. See that all the x values are included. So x is an element of all real numbers. And then the range. Y is an element of all real numbers such that, so the curve goes, sort of oscillates between 0 and negative 2. So we'd say that negative 2 is less than or equal to 2y, less than or equal to 0. And then for the exponential function, the domain, x is an element of all real numbers, again, and the range, y is an element of all real numbers such that y is less than 0. Okay, so because it's not less than or equal to, just less than, because the exponential functions have a horizontal asymptote at y equals 0. Okay, and so your work for today, or sorry, for tomorrow in class, is pages 2 to 3, 1 to 7, and applying what you know, football quadratic exercise. Okay, see you in class.